Hello, my name is John Moyer, and I want to welcome you to the NIH Office of Disease Prevention's Methods Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions, to promote the use of the best available methods, and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar via the chat pod. You'll need to open the pod by hovering your cursor at the bottom of the Zoom window and then clicking on the chat icon. Please direct your questions to hosts and panelists. We will open the floor to questions that have been submitted via the Zoom chat pod at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in a few weeks. Lastly, we would appreciate your feedback about today's webinar. Upon closing, you'll be asked to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, Dr. Moyer. Today's speaker is Dr. Brennan Kahan. Dr. Brennan Kahan is the Principal Research Fellow at the Medical Research Council Clinical Trials Unit at the University College London. His research program is focused on developing methods to improve the design, analysis, and reporting of randomized trials. His major research interests include using estimands to improve the interpretability and validity of randomized trials, evaluating statistical methods for complex trial designs, such as cluster, non-inferiority, factorial, and re-randomization trials, and improving the reporting of randomized trials. His recent methods and research includes the development of the Consolidated Standards of Reporting Trials extension for factorial trials, developing estimands and robust estimators for cluster randomized trials, and evaluating and comparing estimation methods for different intercurrent event strategies. It's my pleasure to welcome Dr. Brennan Kahan.
Well, thank you very much. I am very delighted to be here. So today I'm going to be talking about informative cluster size and what the implications it has for the way that we think about designing and analyzing cluster randomized trials. So I'm going to start off giving a bit of background to the issue before getting into exactly what informative cluster size is, and more particularly, what sort of impact it has on our choice of research question or estimand and choice of statistical analysis. And then I'll get into what all of this means for the way that we think about running cluster randomized trials as we go forward. So cluster randomized trials or group randomized trials, these are trials where instead of randomizing individuals to one treatment or another, we randomize groups of individuals. So we randomize entire hospitals, schools, or villages between intervention and control. So every participant within a cluster then receives the same treatment. And some of the reasons we might think about doing a cluster randomized trial is if we have an intervention that's being implemented at the cluster level, so everyone within a cluster has to receive the same intervention, or if we want to avoid the risk of contamination where two kind of patients at the same cluster, if one's assigned intervention and one control, the control patient might get exposed to the intervention inadvertently. Now, one of the main challenges in cluster randomized trials is that patients within clusters tend to be correlated. This is generally denoted by the interclass correlation coefficient. And what this means is that two patients in the same cluster are more likely going to be more similar to each other than they will be to a patient in a different cluster. So you can see that in this little figure in the bottom right-hand corner of the screen, where we have two patients in the red cluster. They're going to be more similar to each other than they would be to patients in the blue cluster. And I think, practical implication, or at least one of the practical implications of this within cluster correlation, is that most of these standard statistical methods that we use to analyze individually randomized trials aren't going to work. And the reason for that is those methods typically assume that all patients are independent. And when that isn't true, those methods are going to give us the wrong answer. So when thinking about cluster randomized trials, we need to use an analysis method that allows for this within cluster correlation. So that respects the kind of clustered structure of our data. And it turns out there are actually quite a few different methods available to account for this within cluster correlation in cluster randomized trials. So some of the common ones are listed up here. So I think probably the two most common methods are generalized estimating equations, GEEs, and mixed effects models. And these are broadly two different ways of allowing for within cluster correlation within our analysis. So GEEs do that by allowing us to specify what we think the correlation structure is going to be. So we can assume, for instance, an exchangeable correlation structure, which just means that we assume that patients within a cluster are all equally correlated, but they're independent from patients in different clusters. The other common approach, mixed effects models, that's just a way of essentially fitting a random interceptor cluster, which sort of imposes a similar type of correlation structure to GEEs. Although those are the two most common methods of analysis, there are some other options that do kind of make their way into cluster randomized trials fairly regularly. So the analysis of cluster level summaries, this is where we would just take a sort of average outcome within each cluster. So you end up with a single data point per cluster, and then you perform the analysis on these cluster level summaries to get an overall treatment effect estimate. And the final method is something that I think is probably at the moment a bit less common or a bit less commonly used in trials, but is going to become important a bit later in this talk. And this is called independence estimating equations, or IEEs for short. And what this means is just that we're using a sort of model that makes a working assumption that patients are independent even in the same cluster. Now, we know in a cluster randomized trial, this assumption is going to be wrong. We know that there probably is going to be within cluster correlation, but it turns out this method corrects our standard errors to allow for that sort of clustering structure. So even though it's making that kind of assumption or working assumption of independence, we're still going to be able to get the right answer. Now, to make this even a little bit more complicated, it turns out for each of these methods, there are different ways to implement it, typically through different types of weights allocated to patients or to clusters. So when thinking about a choice of analysis for cluster randomized trials, there really are a lot of different options. And I think one of the things that we're, slowly learning is when thinking about choice of analysis, we need to consider the impact of informative cluster size, because this can impact both the research question that some of these methods are answering, as well as the performance of some of these methods. So informative cluster size, it's a bit of a technical term, but all it really means is that outcomes or treatment effects might be different for smaller clusters as compared to larger clusters. So I'll give you an example of what I mean using a very simple example with these two clusters here. So we can see in the first cluster, we only have 4 patients, so it's a very small cluster, and the second cluster is a very large cluster with almost 40 patients. So one type of informative cluster size might be if outcomes are better in smaller clusters as compared to larger clusters. So here in this example, if we have some sort of adverse event, we can see here that patients in the small cluster actually have better outcomes. So they only have a 20% chance of the adverse event, whereas patients in the larger clusters are having on average worse outcomes because they have a much higher chance of experiencing that adverse event. Another type of informative cluster size is when it's actually the treatment effect itself, or patients' response to treatment, that is different between bigger and smaller clusters. So it might be that patients in smaller clusters tend to respond better to treatment and have larger treatment effects than patients in larger clusters. So in this figure, we can see patients in the small cluster have an odds ratio of 0.5. So the treatment's working much better at preventing that sort of adverse outcome than it is for patients in the larger cluster who have an odds ratio of 0.8. So a much lower response to treatment. And these sorts of informative cluster size can happen for different reasons. So it might be that there are differences between the types of patients who would present to larger or smaller clusters. So it might be some patients in our trial have higher socioeconomic status, and those patients are more likely to present to smaller or more exclusive hospitals. And so this sort of kind of baseline characteristic of these patients, in this case, higher socioeconomic status, those types of patients tend to have better outcomes anyway. So it's nothing to do with the cluster itself. It's just patients who tend to have better outcomes tend to go to smaller clusters. Or it might be that the cluster itself is actually exerting some influence on the patient's outcome. So it might be that larger clusters have different processes of care than smaller clusters. So that might be affecting patient outcomes. Or it might be that the intervention itself is easier to implement in smaller or larger clusters. So in this example, if we have an intervention that's very time intensive to implement, so it requires clinicians to go to every patient in the hospital and spend a long time implementing the intervention on them, it might be that that's easier to implement in smaller clusters where clinicians might have fewer patients to see, rather than larger clusters where they have more patients to see and so have less time to implement the intervention. So here it might be that the reason treatment effects are larger or outcomes are better in the smaller clusters is just there's more time to implement the intervention properly, so we're seeing a better treatment effect. So the reason all of this matters, again, it's that informative cluster size can affect the question being answered by some of the different methods of analysis that we might use for cluster randomized trials, but it can also actually affect how well some of these methods are working. So it can potentially introduce bias for certain methods. So when thinking about designing a cluster randomized trial, we need to think through how informative cluster size might be affecting the conclusions that we're getting from different methods of analysis to make sure that we're using the right method. So I'll give you an example of why this matters in practice. So the RESTORE trial, it was a cluster randomized trial in pediatric intensive care units, and it was comparing whether protocolized sedation can improve outcomes for critically ill children. So this was a cluster randomized trial in 31 clusters and enrolled almost 2,500 participants, and it had quite a wide range in cluster sizes across the different clusters. So the smallest cluster only enrolled 12 participants, whereas the largest cluster enrolled, I think, more than 20 times that amount at 272 participants. So what the outcome I'm going to be focusing on here is one of the secondary safety outcomes, which is post-extubation stridor. And this is essentially a bad outcome. So it's indicating that the intervention might be causing harm or that harm is happening to the patient. So here in this table on the right-hand side, I said earlier, we have a lot of different options for how to analyze cluster randomized trials. And this table is showing through the results from some of those different options. So the method in the left-hand side of the table, that doesn't really matter so much for the moment. But I think what's important to take away from this table, or at least I think the thing that jumps out to me the most, is depending on the specific method of analysis that we choose here, I think it can really affect our interpretation of the trial results. So here, an odds ratio larger than 1 is denoting that the intervention is possibly causing harm. So if we see an odds ratio of 2, that would indicate intervention is potentially doubling the odds of this sort of adverse outcome occurring. So if we were to choose, one of these particular methods of analysis, it might actually show, I think, moderately good evidence that the intervention is causing harm. So we might see an odds ratio of 1.8 with a statistically significant p-value. So indicate, maybe the intervention is causing an increase in these adverse outcomes. Whereas if we were to choose a completely different method of analysis, we might come to the conclusion that there's really not much of a signal of harm here. So for instance, some methods of analysis would give an odds ratio of about 1.38, so quite a bit smaller than 1.83, with a p-value of 0.17. So I think most of us kind of seeing that in a trial report or table of results wouldn't necessarily think that was good evidence of harm. So depending on which specific method of analysis we use, we might come away with slightly different views of how well or how badly the treatment is working. And I think one of the reasons that we're getting such diversity of results here is because I think there's some evidence to suggest there's informative cluster size in this trial. So outcomes or treatment effects are different between larger and smaller clusters. And this informative cluster size means that some of these methods of analysis are actually answering quite different types of research questions or estimands. And some of these methods might be kind of affected by informative cluster size in the sense that some level of bias is being introduced. So to put it another way, I think when we think we might have informative cluster size in our trial, this means we need to think quite carefully about what our research question actually is and how we would choose our analysis in order to best answer that research question. So I'm going to start off talking about the first of those two issues, which is the impact of informative cluster size on our research question. And to do that, I need to talk a little bit about estimands. So I think estimands are often seen as these sort of quite complicated or technical things, but an estimand is really just a description of the research question we're trying to address in our trial. So it's sort of trying to tell us what our study is trying to estimate or what our study is trying to answer. So we can see in this table in the bottom right-hand corner of our screen an example of an estimand for a trial in asthma. So here the estimand is just telling us which patients we're interested in estimating the treatment effect for, which versions of treatment we're interested in comparing, what the endpoint is that we want to compare treatments on, how we're kind of summarizing these differences. So is it a difference in means or a difference in proportions, that sort of thing. And it's also telling us that here we're interested in understanding what the treatment effect would be in a hypothetical setting where patients hadn't stopped treatment early or received any additional treatment, such as rescue medication. And the reason that we think about using these sorts of estimands is really to help increase clarity. So it's a way of telling other people what it is that we're trying to estimate in our trial or what question we're trying to answer, so they can understand whether that's relevant for them. But it's also helpful for us as investigators to understand our research question, because this can help us make sure we're designing and analyzing our trial in a way that allows us to answer that question robustly. Now, one of the challenges in cluster randomized trials, over and above individually randomized trials, is there are additional types of research questions that we can answer in cluster randomized trials. So there are additional things that we need to think about. So one of these kind of distinctions that's been around in the literature for quite a while is the distinction between marginal or cluster-specific treatment effects. And that's not something I'm going to touch on much today. What I am going to go over is the difference between what's called participant average and cluster average treatment effects. And this is something that can be affected by the presence of informative cluster size. So the difference between participant average and cluster average treatment effects is really in how individuals and clusters are weighted. So I'll show you what I mean using this very simple fictional example in the table in the bottom right-hand corner of the screen. So in this example, we only have 4 clusters. The first 2 clusters are very small clusters, so they only have 10 participants. The last 2 clusters are very large clusters, so they have 100 participants. And the column on the right-hand corner of the table, that's showing us what the true treatment effect in those clusters is. So it's showing us the average difference in outcomes if all patients in the cluster had been assigned intervention versus if they had been assigned control. So that's the average treatment effect in those clusters. And we can see that the 2 small clusters have a small average treatment effect of 2, whereas the 2 larger clusters have a larger average treatment effect of 5. So for the participant average treatment effect, this is where we give equal weight to each patient or each participant. So here, we know that there are 20 patients in small clusters, each with a true average treatment effect of 2. We know there are 200 patients in larger clusters with an average treatment effect of 5. So for the participant average treatment effect, we just take an average over all those participants, and we get an overall participant average treatment effect of 4.7. And the reason why we might be interested in calculating this sort of participant average treatment effect is it tells us kind of how much the intervention works for the average participant, or as an average across participants. So if we were doing a cluster randomized trial in a school, for instance, to test whether an intervention applied at the school level improved test scores for children, the participant average treatment effect would tell us how much test scores improved children's results on average. Now, the cluster average treatment effect, this is where each cluster gets equal weight. So in this example, we know there are 2 clusters with an average treatment effect of 2. There are 2 clusters with an average treatment effect of 5. So we can take the average across those 4 clusters and get an overall cluster average treatment effect of 3.5. And this is telling us how much the intervention, or how well it works at the level of the cluster. So it tells you how much are test scores at a school, the average school, likely to rise. And it turns out when we have informative cluster size, so when outcomes or treatment effects differ across small and large clusters, the participant average and cluster average treatment effects can be different. So in this example, there's, I think, a moderately large difference. So the participant average treatment effect of 4.7 and a cluster average treatment effect of 3.5. And the reason that we're getting these different treatment effects here is due to the informative cluster size, where we know there are only 20 participants from small clusters. So in the participant average treatment effect, those 20 participants are getting very little weight compared to the cluster average treatment effect, where we're actually giving those 20 participants almost half the weight because they belong to 2 of the 4 schools. So the cluster average effect is sort of upweighting the treatment effect from these smaller clusters. So I think one of the main implications of this is that when we're thinking about running a cluster randomized trial, we need to think through which of these 2 questions we're interested in. So are we interested in the participant average treatment effect or the cluster average treatment effect? And I think it's not going to be the case that there's one right answer, so that the participant average effect is more relevant or better than the cluster average effect, or vice versa. I think the choice of which of those 2 questions we're interested in is really going to come down to the individual study. So it's going to come down to potentially what our clusters are, what our outcome is, who we want to kind of think about using the results for. So I think one of my rules of thumb is that if we're interested in understanding how an intervention impacts individuals, we'd often be interested in the participant average effect. And if we're interested in understanding how it impacts on the clusters, we'd be interested in the cluster average effect. So going back to our school-based example, if we want to understand how well the intervention kind of improves test scores across participants or across students, would be interested in the participant average effect. And this might be something that's more relevant for students or for their parents. If we're interested in understanding the impact on the schools themselves, so if, for instance, we're a school administrator, we want to know, well, how much is this intervention going to improve results at my school? Then that's something that would be best answered using the cluster average effect. Now, I think one of the follow-on implications of this is, given that we can answer different types of questions in cluster randomized trials, we need to make sure that when we choose a method of analysis, we're choosing a method that answers the question that we want to ask. So if we're interested in a participant average treatment effect, then we don't want to use a method that estimates a cluster average treatment effect, because then we might be getting bias for the question that we're really interested in. So it turns out that if we're interested in estimating a participant average effect, the 2 ways that we can do that are the analysis of cluster level summaries or independence estimating equations. And we need to make sure that we're implementing these in the right way. So there are different ways to implement them based on how we weight patients in the analysis. So we need to make sure we're using the right weighting scheme. It turns out for the cluster average treatment effect, we can actually use the same two methods, so analysis of cluster level summaries and also independence estimating equations, but we need to make sure we implement them in a different way, in a way that's appropriate for cluster average effects and is using the correct weighting for that estimand. Now, you'll notice that I've not mentioned anything about generalized estimating equations or mixed effects models and whether they estimate participant or cluster average effects, which might be a bit odd because these are the two, I think, most commonly used methods of analysis in cluster randomized trials. And the reason I haven't is to do that, we need to think about how well these models work in the presence of informative cluster size. So when thinking about estimating either the participant average effect or the cluster average effect, we need to give equal weight either to each patient for the participant average effect or equal weight to each cluster for the cluster average effect. And it turns out that generalized estimating equations and mixed effects models tend not to give equal weight to either patients or to clusters. Instead, they end up typically weighting each cluster by its inverse variance. And this can actually be quite a useful thing to do because weighting by inverse variance, it's going to lead to, I think, the most precise estimate of treatment effect. So by doing this, these methods tend to give us more precise answers with narrower confidence intervals. So we're getting a kind of better sense of the true value of the treatment effect. Now, I think the issue with this, or the potential issue, or practical implication, is these models tend to upweight treatment effects from smaller clusters and downweight treatment effects from larger clusters. Now, if there's no informative cluster size, that means that the treatment effects in small and large clusters are going to be the same, and then actually GEEs and mixed effects models are going to work perfectly well. So they're going to be unbiased for both the participant average and cluster average effect, and potentially give us more precise estimates than other methods. But if that's not the case, so if there is informative cluster size, then it might be the case that both of these methods are actually going to be biased for both the participant and cluster average effect because they're getting the weighting scheme wrong for these two estimands. So this is an example of bias from these methods. This is a figure showing the bias for the participant average effect when there's a very extreme form of informative cluster size. So this is much more extreme than I think we'd ever see in practice. So I don't think we'd ever expect to see kind of that degree of bias, but it's really just for illustration. So this figure, it's based on simulated data sets. So it's based on a setting with 30 large clusters, each with a very small treatment effect, 30 small clusters, each with a very large treatment effect. And so what we can see, this has a very strong degree of informative cluster size. And what we're seeing is that mixed effects models and GEEs are both showing substantial degrees of bias. So upwards of 40, 50% bias. And the other thing we're seeing is that as the within cluster correlation, so the ICC interclass correlation coefficient, which denotes how correlated individuals within a cluster are, so as that correlation increases, the bias in these models is getting worse. So kind of the higher degree of correlation we're seeing, the worse these models tend to perform if there is informative cluster size. Conversely, we are also seeing kind of results from independence estimating equations here in green, and these models are working perfectly well in this setting because they're not affected by informative cluster size. So going back to the RESTORE trial, I think we can now make a little bit more sense of this kind of difference between results from the different methods of analysis. So I think to a large extent, not exclusively, but quite a bit, these results are potentially being driven by informative cluster size. So if we look at small clusters, so clusters with fewer than 100 participants, we're getting an overall average odds ratio of 1.15, so not much evidence of anything going on. Whereas for the larger clusters, so clusters with greater than 100 participants, we're seeing much larger treatment effects, an odds ratio of 2.26. And so what this informative cluster size is potentially driving is quite large differences between the participant average estimands and the cluster average estimands. So for each of these two estimands, we can split them also by whether the treatment effect is marginal or cluster specific. So for the marginal participant average estimand, we're getting an estimate of an odds ratio of 1.65, whereas for the cluster average odds ratio, it's only 1.38. Similarly, for the cluster-specific participant average estimand, we're getting an overall result of 1.83, so quite a large indication of potential harm, whereas the cluster average effect is again only 1.51. So here we're getting much larger effects from the participant average estimates compared to the cluster average estimates. And I think the likely reason for this is if the treatment is kind of has a smaller treatment effect in the smaller clusters, then the cluster average treatment effect is kind of upweighting this smaller treatment effect from those smaller clusters. So it's sort of giving a lower indication of overall harm than the participant average treatment effect. And we can see that the two participant average treatment effects, in addition to being larger than the cluster average treatment effects, also have statistically significant p-values. So they're showing, I think, a larger indication of potential harm from the intervention. Now, it's not just the difference between the two estimands, so the difference between participant average and cluster average effects that's kind of leading to these differences, but there are also differences within kind of different methods of analysis for the same estimand. So here for the participant average marginal effect, we can see independence estimating equations, which isn't affected by informative cluster size. It's giving us an odds ratio of 1.65 and p-value of 0.04, whereas generalized estimating equations is giving us a slightly smaller odds ratio, not that much smaller, but just, I think, smaller enough that it might not change our interpretation, but might kind of skew things a little bit. And that's potentially happening because informative cluster size might be introducing a little bit of bias into results from this method. Similarly, for the participant average cluster specific estimand, we have the cluster level analysis, which again isn't affected by informative cluster size, as giving us a much larger odds ratio of 1.83, which is statistically significant, compared to a mixed effects model, which is giving us a smaller odds ratio. And again, this might just be due to informative cluster size, which is introducing a little bit of bias into the mixed effects model. So I think one of my takeaways from looking at the reanalysis of the RESTORE trial is if we're interested in a participant average effect, which I think in this case we probably would be, because we want to know kind of, if we were to introduce the intervention, what is its impact on patients? So are we kind of improving outcomes or kind of causing harm on average across patients? So if we get the wrong estimand, so if we were to kind of use a method which targeted a cluster average effect here, I think we could potentially be masking some of that potential harm from the intervention. Or if we were to use a method which potentially is being affected by informative cluster size, again, that might kind of challenge our interpretation a little bit. So what does this mean kind of going forward when we think about designing and analyzing cluster randomized trials? I think the first thing we need to do is think about, I think our aim for not just cluster randomized trials, but any trial is really to make sure we're getting good answers to the right questions. And I think informative cluster size poses a challenge for both parts of this. So it can make understanding what the right question is a little bit more challenging, but can also make getting an estimate of that question also a little bit more challenging as well. So I think the first thing we need to think about when running a cluster randomized trial is what our research question is. So are we interested in a participant average effect or a cluster average effect? And again, there's not necessarily going to be any one right answer to this. It's going to depend really on what question we want to get out of our trial. And that will depend on a number of things, such as type of study and all those sorts of things. I think the other thing we need to think about is once we've kind of settled on our estimand or research question, we need to make sure we're choosing an analysis method that's going to give us a good answer to that question. So if we are interested in a participant average effect, we shouldn't use a cluster, a method of analysis that's targeting a cluster average effect and vice versa, because if we do, we're going to get bias for the question that we actually want to answer. And I think we also need to consider the likelihood of informative cluster size when choosing our method of analysis. So if we're running a trial where we think informative cluster size is likely, then we might not feel comfortable using mixed effects models or generalized estimating equations because this informative cluster size might introduce bias into those methods. So here we might want to use independence estimating equations or analysis of cluster level summaries instead, because these aren't affected by informative cluster size. However, if we think kind of at the outset of our trial that informative cluster size isn't going to be likely, then we might be very happy to use mixed effects models or generalized estimating equations, because we know if there isn't informative cluster size, they're going to give us the right answer. So they're going to be unbiased, but they're also potentially going to be more precise than other methods of analysis. So we're getting a kind of better estimate of treatment effect. But I think one of the challenges is it can be very difficult to definitively rule out at the design stage the possibility of informative cluster size. So we can say, based on the type of intervention or types of clusters, we don't think informative cluster size is going to be likely, but it's hard to say for sure that it's not going to happen. So when we are running a trial where we're using mixed effects models or generalized estimating equations, it can be useful to think about doing some sensitivity analyses just to make sure that conclusions aren't being affected, if informative cluster size does happen. So the summary is, I think when thinking about cluster randomized trials, we need to start with our research question, so our estimand, and part of that is thinking through whether we're interested in the participant average effect or the cluster average effect. We need to think about choosing a method of analysis that is aligned to that research question, so is able to answer the right question. And part of that is thinking through whether informative cluster size is likely to occur in our trial, because that's going to maybe motivate what the right method of analysis is. And when using methods such as mixed effects models or generalized estimating equations, it can be useful to run sensitivity analyses to consider the potential impact of informative cluster size on results. So before I finish, I just want to flag up a few resources that might help you kind of navigate some of these issues when you're running your own cluster randomized trials. So this paper came out last year. So this describes what informative cluster size is, as well as potentially what might cause it, its impact on choice of research question and analysis, and also goes a little bit into the distinction between participant average treatment effects and cluster average effects, as well as a little bit of guidance on things to consider when choosing between them. So this second paper is much more, I think, focused on the statistical analysis aspect. So it does talk about the distinction between the different estimands, but what it really does is for each kind of estimand option, it goes through the different kind of choices of analysis that we have to estimate that estimand, as well as the assumptions it makes. So it's one of those things where if you have a particular estimand in mind, this paper can help you figure out the best way or the different options in terms of running the analysis. So the output of that in this paper, it turns into this quite large and slightly unwieldy table, where on the left-hand side, we have kind of the different estimands with the description of each, and then for each estimand, we go through the different methods of analysis that target that estimand, as well as how they can be implemented, as well as the assumptions that they make. So before I finish, I just want to briefly mention future work. So I think it's fair to say that I think in the cluster trials community, or at least for myself, informative cluster size isn't something that we've been thinking about for too long. So I think to a large degree, we're still learning about it and trying to kind of understand more about how to handle it in cluster randomized trials. So I think that does motivate the need for more work to understand how common informative cluster size is in cluster randomized trials. So is it affecting, 1 in 10 trials, 1 in 100, or 1 in 2? Because understanding that sort of prevalence, I think, is quite helpful for understanding, its risk, likelihood, and, whether how much I guess we need to worry when designing trials. I think we need a bit more work to understand the potential impact it can make in practice. So I think from the restore trial example, we know it can potentially affect interpretations depending on which method of analysis you use. But again, it would be useful to understand, how often these sorts of things are occurring where informative cluster size is really challenging our interpretation. And to do this, I think one of the useful things would be better ways to kind of test for and identify informative cluster size within real trials. And I think one of the other things that would be quite useful, kind of stemming from all this work, is potentially looking at new estimators or new methods of analysis based on things like mixed effects models or generalized estimating equations, which can sort of maintain the efficiency gains from those models while still being robust to informative cluster size. So before I finish, I do just want to give a few acknowledgements. So all of the content in this presentation has been joint work with many other people. And it really, I think, would be remiss not to point out that everything in this presentation really has built on decades of work in cluster randomized trials that's come before. Thank you very much to the Mind the Gap team for the invitation to present, and thank you all for listening. I'm happy to take any questions.
Thank you so much for a very clear and well-organized presentation. You've gotten many compliments in the chat box, as well as a whole bunch of questions. So we can get started. The first question I was going to ask you was how common this problem is, but you said, well, we need more research to answer that question, so we probably don't know. Do you have any sense of how common this is? Informative cluster
Yeah,
size?
I don't think at the moment we really do have an idea of, whether it is, 1 in 10 trials or 1 in 10 outcomes. I think, from the few reanalyses we've done, I think we've seen it in more than one trial, or we think we've seen it in more than one trial. It can be a bit difficult to test for. But I think we kind of do need that large scale approach to kind of understand, out of 100 trials, is it going to be 10, 20, 30 that are affected? So I think the best we can say at the moment is we know it can happen. We know it can affect results, but we don't quite know yet how often it will do those things.
Right. So a common question that I'm seeing from our audience is, how do we know whether there is informative cluster size in the trial that we're running, or perhaps the trial that has just concluded that we're managing? And there's sort of two questions that come out of this. One, people want to know what's the best way to find out if there's informative cluster size. But my concern when I think about that question is, well, gee, should we be looking at that before we choose an analytic method? I thought we were always supposed to specify the analytic method in advance. So that's a complicated pair of questions, but interested in your thoughts.
Yeah, thank you. It's something that I think we've been grappling with a little bit. So I think I'll answer your second question first. And I think that's maybe one of those questions that if you ask different people, you might get slightly different views. My personal view is I wouldn't necessarily recommend testing for informative cluster size and then choosing, which method to use based on that test. Just because I know in other areas, it's quite often the case that those sorts of, initial tests to help you choose the method of analysis do often go a bit wrong. So they can often, just by doing that test, introduce bias or a kind of inflate type 1 error rate. And I think particularly in cluster randomized trials, where we often have a very small number of test clusters, I would worry a bit just that any sort of test like that would have quite low power to detect informative cluster size. So it wouldn't really necessarily be a robust way to rule it out. I think the first part of the question in terms of how do we test for this or evaluate this in our trials, I think at the moment we don't yet have really good ways of doing this. I know some people are working on a test for this that will kind of make things a little bit easier, but I think at the moment the best way we have of kind of evaluating this in individual trials is just comparing estimates from the participant average effect and the cluster average effect. Because we know that if there is no informative cluster size, we know that kind of these two should be equivalent on average. So if there are very large differences, that might be a sign of potentially things being affected by informative cluster size.
Yeah, I certainly share the concern about using a test to guide thinking about analysis methods, particularly when the test might be underpowered. Many people think, oh, well, let's test to see if the interclass correlation is different from zero. That's the classic one. And I've always hated that approach. I think it's a very bad idea. And sounds like you have a similar view here. So if we're concerned that it might be an issue, better to perhaps propose an analysis that allows for it. And if it's not there, it's not going to hurt us too badly. But if it is there, then we've got an analysis method that can accommodate it. Can you comment on how much of an issue informative cluster size is if the analysis adjusts for factors that are related to cluster size and treatment effects? So can we use regression adjustment, for example, to make the impact of informative cluster size go away or at least be reduced?
Yeah, I think that's a really good question, and I think something we probably need to look at a little bit more going forward. I think in theory, if there are baseline factors that might kind of explain informative cluster size. So in example, in one of my earlier slides, I gave the example of socioeconomic status actually explaining informative cluster size, whereas people with higher socioeconomic status went to smaller clusters and then also had better outcomes. So in that sort of example, if we were to adjust for socioeconomic status, I think that actually probably would kind of break the informative cluster size impact. And then actually might be very well able to use generalized estimating equations or mixed effects models and kind of remove any bias from informative cluster size for those methods. I think one of the potential challenges with that is just knowing whether we have kind of fully adjusted away any informative cluster size, as well as kind of things like making sure we've gotten the, association between those factors and such as socioeconomic status and outcomes correctly specified. So I think to answer the question, short answer would be, yeah, I think in theory that could work. I don't know that it's, and probably something good to think about and maybe implement just as a, way to help us protect us a little bit. I don't know that's necessarily going to be foolproof just because it is very difficult to know that we've kind of fully adjusted it away.
Thank you. Sorry, I'm trying to track all the questions in the chat box and as well as listen to your responses. So I'm busy over here. If at the design stage the clusters are all of similar size, can we assume that informative cluster size does not exist?
Yeah, so again, a very good question, and I think that is spot on. So if you were to have, a trial where all of your clusters had 10 people, then I think by definition, there cannot be informative cluster size because there's no variation in cluster size. So in that case, we don't need to worry about informative cluster size at all. We know that we're fine. More broadly, it's probably quite rare to have a trial with, exactly 10 patients in every cluster. But if we have a trial with very little variation in cluster size, say, most of the clusters have between 9 and 11 people, there still could be informative cluster size, but it's probably not going to be that strong in the sense that because there's such little variation in cluster size, it's not going to have a large impact on results. So in that sort of setting, I think we can be a lot more confident that informative cluster size isn't going to be causing problems for our analysis methods.
Yeah, years ago, when I was running school-based studies, I was concerned about having large schools and small schools in the same trial. And I reached out to a friend and colleague, Leslie Kish, who's a survey sampling expert, no longer with us, but his 1965 survey sampling text was a classic. And I asked his advice, and he said, David, if the largest school is no more than about twice the size of the smallest school, you're probably okay and don't have to worry about it. But if the variability is greater than that, it would be a concern. And I followed that rule of thumb for years, avoiding recruiting schools that varied more than about 2 to 1. Does that advice seem reasonable to you, or do we know more now and you can offer better advice?
Um, yeah, I would need to think about that. I mean, I guess again, it sort of probably comes down to the research question. So if I were doing, a trial in the UK in schools, um, I don't know that I think there probably would be a bit more variability than that in, across the schools in the UK. And I guess I might be a bit hesitant to kind of limiting the schools that we enroll to, have that maximum variation of, 2 to 1. Just I guess worry that we're, excluding some schools that might be quite important to include because we are interested in the effects in those schools. But I guess the flip side of that is, when we do that, we are getting a much wider variation in cluster size, and so potentially opening ourselves up to the danger of informative cluster size a little bit more. So I guess my personal approach, which I think probably wouldn't be for everyone, but I would probably be quite happy to kind of have that larger variation across the schools, but just maybe try to go with an analysis method that was robust in case we did get that sort of informative cluster size.
Quite understandable. Um, so what about the number of clusters in the trial? Is informative cluster size equally important in studies that have lots of clusters as it is in studies that have a small number of clusters? The variability in the number of clusters is huge in trials these days. They all used to be fewer than 20 total, and now we're seeing trials with 50, 100. What are your thoughts about the size of the trial overall in terms of the number of clusters?
Yeah, I think that unfortunately, it's not one of those things that where we recruit a larger number of clusters, the problem goes away. I think it does affect larger trials in the same way as smaller trials. So yeah, it's something I think we need to think of in the same way for both, really.
Is there a way to in the way that the code is written to use GEE or mixed models um, that will avoid the bias that you've identified, or is it inevitable if you're using GEE or mixed models with in the presence of informative cluster size?
Yeah, so with GEE, this is something I didn't say in the talk, but I think is very important to point out. So with GEE, you can implement quite different types of GEE models depending on which correlation structure you choose. So the one I've focused on in this talk is GEEs with an exchangeable correlation structure, which I think is probably one of the more common versions in cluster randomized trials. And it's that version that's going to have problems with informative cluster size. If we were to use GEE with a different sort of correlation structure, so for instance, using a independence correlation structure, then actually that's just another way of implementing an independence estimating equation, sort of using a GEE wrapper. So that's actually going to be perfectly fine. So yeah, I think a really good point that GEEs, there is actually a distinction between GEEs with an exchangeable correlation structure, which is affected by informative cluster size, and GEEs with an independence correlation structure, which isn't, and it's just another way of doing independence estimating equations. In terms of mixed effects models, I don't know of any kind of standard way of, coding that or kind of changing that so that informative cluster size wouldn't be an issue. Although I do know there is a kind of ongoing area of research looking at kind of developing, model robust versions of mixed effects models where you're able to get a kind of robust answer even in the presence of informative cluster size. So maybe kind of at some point in the future, we'll have versions of that we can use.
Great, thank you. There's a lot of interest in whether informative cluster size is an issue in other kinds of designs besides parallel cluster randomized trials. People have asked, well, what about cluster crossover designs, or what about step wedge designs? And a couple of people have asked, are these issues applicable to observational studies where we're not talking about trials at all?
Yeah, really interesting questions. So I think this issue of informative cluster size will have implications for other types of cluster designs. So I think it will have implications for cluster crossover designs and for stepped wedge designs. Although I think it might kind of affect models in slightly different ways. So it's not necessarily the case that, generalized estimating equations with a exchangeable correlation structure will always be biased under kind of every type of informative cluster size in a cluster crossover trial. So I think the cluster crossover design and step wedge design, I think it is important to think through kind of implications of informative cluster size, but there might be additional considerations there for what the right choice of analysis is. In terms of observational studies, I think the answer is yes. I think informative cluster size can kind of affect those studies in exactly the same way as it would a cluster randomized trial, assuming that we have that same sort of clustering structure in our observational study. So it is something that would be important to think about there. I guess the one potential difference is in a cluster randomized trial. I think the reason that we get maybe issues a little bit stronger than in individually randomized trials is because all patients within a cluster get the same treatment. If in the observational study we're kind of having a mix of patients within each cluster getting different treatments, I think that might kind of change the implications a little bit. But that's maybe something that I would need to think a little bit more on.
Yeah, there is another study design that we haven't talked about yet that is sort of in between the cluster randomized trial and the individually randomized trial. I call them individually randomized group treatment trials. Some people call them partially nested designs. So randomize individuals to study arms, but then in the intervention arm, people receive at least some of their treatment from a shared intervention agent or in a small group format. And clustering develops over time. It's not present in the beginning, but it can develop over time in those kinds of trials. I've not seen a thing about informative cluster size in that context, and I wonder if you have, if you have thoughts about the role it might play in that kind of design.
Yeah, I think that's a really interesting point. And I think it potentially could cause issues in those types of designs as well. I don't think, to my knowledge, there's been much or any kind of research on informative cluster size in those types of individually group randomized trials. But that is something that I think we're going to be looking at soon to kind of see what sort of impact we might expect there. As well as how common informative cluster size might be in those designs. So hopefully sometime in the future we'll have a better answer for you on kind of the impacts and how common it is.
I want to thank you so much for a lovely presentation and a fun discussion. There are many more questions that we didn't get to, so I hope you will be willing, if Dr. Moyer sends them to you, to draft brief responses that we can post on our website so our audience can see responses to the questions that I didn't have time to get to.
course, yeah.
Again, I want to thank you very much for your presentation today, and I'll turn things back over to Dr. Moyer to wrap up.
Thank you.
Thank you, Dr. Murray, Dr. Kahan, and thank you to everyone who participated in today's webinar. On the Mind the Gap website, prevention.nih.gov/mindthegap, you'll find several resources for this talk, including the slides and a list of references. We will also be posting a recording of today's webinar on our website in a few weeks. Thank you and have a great rest of your day.